Chapter 17, aromatic compounds. And up until now, whenever we've talked about aromatic compounds, we always referred to this molecule, benzene. So you're all fully aware of what benzene is, and that it is an aromatic compound. But what you're going to find in this chapter is that there are many, many more aromatic compounds in organic chemistry. And hopefully by the end of today's lecture, you'll be able to identify a compound as being aromatic or not. Sometimes we call aromatic compounds arenes, and they include molecules like benzene and also toluene. And toluene we would have seen a few times in this class. It's used as a solvent in many reactions. You can see that when you have two methyl groups on a benzene ring, we call that xylene, and we have the prefix here ortho. And I'm going to discuss in detail what the ortho means, but I'll tell you right now that it means that you have groups that are 1, 2, like this. So when you have the two methyl groups at positions 1 and 2 like this, we call that ortho positioning. It says here that benzene derivatives were originally isolated from fragrant oils from tree balsam or sap or some kind of tree oil. And the first derivatives of benzene were fragrant. They did have pleasant odors, and that's where the word aromatic came from. Now, as science progressed, many more aromatic compounds were discovered, and most aromatic compounds, in fact, are odorless, have no odor whatsoever, but the name aromatic stuck. And I just want to again remind you, and I think I've told you this a few times in this class, is that aromatic, what aromatic means to a scientist nowadays is that the molecule has stability. So it has some inherent stability, and we're going to discuss where that stability comes from. If you've ever looked up the structure of any prescription medications, maybe just by looking at Wikipedia or the top 200 drugs by sales, generics or brand name drugs, anyhow, you would see that aromatic rings are very commonly found in drugs. And you see all of these benzene rings. We have a benzene ring in this molecule called Lipitor, and I know Lipitor pretty well because I worked for Bristol Myers Squibb when they put that compound on the market. I also worked for Bristol Myers Squibb when they were selling Plavix. It's since gone off patent, and they had invented that molecule before I joined the company. Anyhow, another one is Prilosec. So this is Nexium. You can purchase this by the metric ton or something down at Costco. It's a proton pump inhibitor. So if you have heartburn, and you'll notice that if you look at look at just the skeleton of the Nexium or the Prilosec molecule, you notice that it's pretty close to this one here. Okay, you're like, those look pretty similar to me. So Prevacid was put together by a different company, and it has the same skeleton, and we call that a Me Too drug. So basically somebody jumps in on the bandwagon and says, well, I'll use the same skeleton and I'll modify it slightly, make sure I get out of the patent zone, and there we go, I'll hit pay dirt. Anyhow, another one I want to draw your attention to is this one here, Zyprexia. So this is used to treat schizophrenia, but this part that I'm circling here or boxing in here in green, this is called a benzodiazepine, and many CNS drugs are benzodiazepines. Anxiolytics like Adderall, sorry, not Adderall, Ativan. Adderall is something completely different. Anyhow, Ativan or Rivotril, those are things that are used to kind of calm people down. Anyhow, just something interesting there. So a seasoned chemist will be able to look a lot of times at skeletons and be able to say, well, this kind of drug might be used as a CNS drug. This one might be a diabetes drug, so on and so forth. Anyhow, aromatic rings are found everywhere. They're even found in the coal that's underneath the topsoil on our planet. Okay, so it says coal contains aromatic rings that are all fused together and joined by non-aromatic functional groups. Now, this is just a random segment of showing you what kind of what the structure of coal actually looks like. So you can see it's all these carbon-carbon bonds and carbon-hydrogen bonds. And what happens when all of these carbon-hydrogen and carbon-carbon bonds undergo combustion, they form carbon-oxygen double bonds, which are lower in energy, right? The carbon-oxygen double bond comes from CO2, which, again, that bond is lower in energy. And so energy is released in the form of heat, and that's how we can use coal to generate electricity. Anyhow, kind of interesting. Look at the structure of coal. Well, let's switch to section 17.2 and discuss how we name benzene derivatives. And it says here that benzene is generally the parent name, now keep in mind, it says generally the parent name for monosubstituted benzene. So you have to kind of sort these out in your brain because we're going to look at monosubstituted benzene derivatives. We're also going to spend some time looking at disubstituted benzene derivatives, and we're going to look at, tri, tetra, penta, so polysubstituted benzene derivatives. Anyhow, if you just have, one group on your benzene ring, you would have, if you have a chloro, you'd call that chlorobenzene. If you have a nitro, you'd call that nitrobenzene. You have an ethyl group, you'd call that ethylbenzene. What else? If we had, we could come up with all kinds of examples here, right? If you have, I don't know, if you have this, we would call that isopropylbenzene. It also has a common name, which is cumene. You don't have to have that memorized. If you had, what if you had an iodo, right? What if you had an iodine? That would be iodobenzene. Anyhow, we could do that for a while. But let's move on to the next slide, which covers common names of benzene derivatives. And you are responsible for knowing all of the common names of all 8 of these aromatic compounds here. In fact, some of them you already know. And the reason you have to know these common names is because they are accepted by IUPAC, the International Union of Pure and Applied Chemistry. And in fact, they're also frequently used. So you are actually going to use these when you name some benzene derivatives. And let's go over these quickly. If you have a methyl group on your aromatic ring, this is called toluene. If you have a hydroxyl, that's phenol. We discussed, we compared the acidity of phenol to an alcohol like ethanol. If you have a methoxy group, we call that anisole. If you have an amino group, that's called aniline. If you have a carboxylic acid, it's benzoic acid. This one's kind of an interesting and easy name, is benzaldehyde, right? Because you have an aldehyde here. The next one's not as abundantly clear, but it's acetophenone. So we have an acetyl group on a benzene ring. We call that acetophenone. And the last one is not abundantly clear at all, right? It's just plain old styrene. So when you have a vinyl group attached to your aromatic ring, that's called styrene. And if you're wondering, does that have anything to do with styrofoam? Well, the original styrofoam, the first styrofoam that was produced, was a polymer of styrene. And yes, there is styrene still in styrofoam, but they've put other additives in it because the initial styrofoam, or the first styrofoam that was only made out of just styrene, polystyrene, was, I think, quite brittle, and I don't think it was, as good as modern styrofoam is. Oops, I didn't mean to do that. Okay, well, let's try to get back on track here. Some more about nomenclature of benzene derivatives. It says here that if the substituent is larger than the ring, the substituent becomes the parent chain. So that's kind of a funny way of phrasing it. The substituent becomes the parent, right? Anyhow, so what's it saying here is that when you're naming benzene derivatives, if you have, just like we saw before, if you have a small, son of a gun, if you have a small, why is it doing that? Come on. Try to redraw that. If you have a small chain coming off of your benzene ring, right? The benzene has 6 carbons in it, and the chain here has 2 carbons in it. And 6 carbons is greater than 2 carbons, so that we would call this ethylbenzene, right? Ethylbenzene. But here we have this molecule, we call it 1-phenylheptane because we have 1, 2, 3, 4, 5, 6, 7. We have 7 carbons in the chain, and we have 6 carbons in the ring. And 7 carbons is greater than 6 carbons. And so the aromatic ring, the benzene ring, now becomes a substituent. And when it's a substituent, we call it a phenyl. Excuse me. Benzene rings are represented with pH, not to be confused with pH, okay, that we use to measure puissance d'hydrogène, for the power of hydrogen. That's something completely different. Anyhow, so we use pH to represent phenyl rings. And then this is really old. It's not even mentioned in our textbook, I don't think, is the phi symbol. I think it might have been mentioned maybe in the first or the second edition of our textbook. So this is phi. It's a Greek letter. Anyhow, here you see it in action. I will never, ever use that. In fact, I don't think I've ever used the phi symbol in my life. Okay, so we'll generally use pH. So we have tetraphenyl cyclopentadienone right here, and you can imagine that it's a lot easier to draw this than to throw in all of those aromatic rings. So time savers, right? Scientists like to get the maximum amount of work done for the minimum amount of effort. It's only natural. Okay, let's talk about when we want to name dimethylbenzene derivatives. We call those xylenes. You have to know the structure of ortho, meta, and para-xylene that are shown here. That doesn't look very pretty, does it? Anyhow, you have to know the structures of these molecules. So if we have the two methyl groups in the 1,2 position, we call 1,2 positioning, we call that ortho. It says here the ortho, meta, and para are used for the location of substituents on di-substituted benzene rings. So that means that if you have a benzene ring and you've got, 1, 2, 3 substituents, you can't use para, meta, and ortho. There's always somebody in the class who wants to just throw it on everything, but you can't. Only for di-substituted benzene rings. If they are 1,3 apart, we call that meta. So this molecule is metaxylene or 1,3-dimethylbenzene. And if they are 1,4, then it's paraxylene, and 1,4-dimethylbenzene would be another IUPAC name. So again, all of these names are acceptable. And in fact, one of my students told me, he said, if you look up the names of some of these molecules on Wikipedia, they'll have like 6 different names. Anyhow, kind of interesting there. All right, so ortho, meta, and para, you have to be fully aware of what that means. Here are some other examples. And what you see here is that each one of these molecules has a parent in it, okay? A parent that we learned a few slides ago. If you see what I'm circling here in yellow, that is an anisole, right? So we're going to name this molecule as an anisole derivative, and we assume that the carbon that has the group from the parent, which is the methoxy group, we call that carbon number 1. So this nitro group is at carbon number 2. So this becomes 2-nitroanisole, or you could call it ortho-nitroanisole. The next one, what do we have in it? We have a toluene, right? Here's a toluene right here. And again, we give the carbon with the parent substituent. We give that the number 1. So we have 1, 2, 3 like this. Again, we want to seek to give our other substituent the lowest possible number, 3, as opposed to 1, 2, 3, 4, 5. 3 is lower than 5. And so this becomes 3-bromotoluene or meta-bromotoluene. The next one, we have our benzaldehyde shown right here. And you can call this parachlorobenzaldehyde, or you could call it what? 1, 2, 3, 4. You could call it 4-chlorobenzaldehyde. Either one would be perfectly acceptable. Well, let's look at some more rules about naming benzene derivatives. So the first thing we're always going to do is identify the parent. If it's got one of those common parents that we saw, like styrene or acetophenone, we'll use that. If it doesn't have one of those, well, it's going to be benzene. Then we're going to identify and name the substituents. We'll number the parent chain, assign a locant to each substituent. This is a rule you have to be fully cognizant of by the time you finish organic chemistry, is that you always give the first substituent the lowest possible number. Remember, it has nothing to do with tallying up numbers and getting out a calculator and an abacus and a mainframe computer, nothing to do with that. Just give the first substituent the lowest possible number. Then you list the substituents before the parent name in alphabetical order. You ignore prefixes except for iso, cyclo, and neo. In fact, one of my students pointed out to me, do we ever even use neo in this class? The answer is very, very rarely, if at all. Anyhow, so let's move on and take a look at an example that's shown here. What's highlighted in red is the parent chain, and you should all be able to identify that by now as phenol. And so we assume that the carbon that has the substituent that has the hydroxyl, that's going to be carbon number 1. Now there is a plane of symmetry going down this molecule, so I can number clockwise or counterclockwise. It doesn't matter which way I go. So I have 1, 2, 3, 4, 5, 6 like this. So I have 2 bromines, 1 at carbon 3 and 1 at carbon 5. And so you can probably already guess that this is going to be 3,5-dibromophenol, but let's look at the guided solution over here. Again, we number the parent chain to give the first substituent, the lowest possible number. Again, it's a symmetrical molecule, so it doesn't matter which way you go. Kind of a funny example. And then you list them. You list the substituents before the parent name. So what do we get? We get 3,5 dibromophenol. Not much to it there. I think that's a pretty manageable molecule to name. In fact, a lot of students seem to enjoy the nomenclature of benzene derivatives. So something to pique your interest before we move on. But let's take a look at some examples. Can anybody tell me what parent, if I call this question 1, I call this question 2, and I call this question 3, could anybody tell me what parent is found in the first one? Not a trick question. Yeah, exactly. You're both right. It's benzaldehyde. Okay, so this is some kind of benzaldehyde. Okay, we get that much. What else? We have a chlorine at the 4 position, right? We assume that this is position 1, 2, 3, 4. And so we could call this molecule, we could call it 4-chlorobenzaldehyde. Does anybody have another name that we could use for this molecule? I'll just throw it out there to my students. I know somebody knows the answer. In fact, I'm sure everybody knows the answer. Yeah, thanks. Absolutely. Somebody just wrote para. You're totally right. It would be para-chlorobenzaldehyde. Okay. You want me to do you one even better than that? Is you can abbreviate it as just p-chlorobenzaldehyde. All right. So you can, instead of putting ortho, instead of writing out the whole word ortho, you can just use O. Instead of writing out the whole meta prefix, you can just use M. Instead of writing out para, you can just use P. Those are all perfectly acceptable. Okay, let's take a look at the next one. Number 2, the parent here would be what? Not a trick question. Yeah, absolutely. You guys are all right. Luke, Adriana, absolutely. Okay, it's going to be a toluene. So there's a toluene in here. And that's the part that's identified in black, not toluene. There we go. So we have 1, 2, 3. So we could call this 3-bromo-toluene, or we could call it meta-bromo-toluene. I knew you'd find these easy. What am I doing here? Toluene, there we go. And then the last one, we have a nitrobenzene, or sorry, we have an anisole, sorry, my bad. Anyhow, we have an anisole here that I have circled in red. And so we could call this 2-nitroanisole. That would be fine. 2-nitroanisole. And we could also call that ortho-nitroanisole, like that. Okay, so as long as you can remember or memorize those parent names, you're usually going to be pretty Johnny on the spot with the whole identifying the name, the IUPAC name for any aromatic compound. In the interest of time, why don't we give one more of these a shot? Let's pick the toughest one. So let's pick C. It's tri-substituted. Can anybody help me out with this one? And maybe just identify, we'll start by identifying the parent for C. Yeah, thanks, Andrea. Yeah, the parent for this one is right here, right? It's phenol. Okay, so this is a phenol. And then we're going to number that ring, and we're going to assume the carbon that has the functional group on it. We're going to call that, or the hydroxyl from the phenol. We're going to call that carbon number 1. Then we're going to number it going counterclockwise so that we give the first nitro group the lowest possible number, which would be 2, 3, 4. So this would be 2,4-dinitrophenol. Okay. You can probably, I bet you guys could name the other ones without even like analyzing it. The first one would be 1, 2, 3. So the first one would be 3-isopropyl benzaldehyde. And the next one you have 1, 2. So this would be 2-bromo-toluene or ortho-bromo-toluene. Either one is acceptable. For the first one, it could be meta-isopropyl benzaldehyde. Okay, give me a thumbs up if you follow me on the nomenclature of benzene derivatives. Excuse me. Cha? All right. Thanks, Liam. Thanks, John. Gang. Everybody who shows up to class on what's today? Wednesday? All right. The next one is just telling us to draw some structures. Not much more here. So maybe I'll just do the first one quickly. it says 2,6-dibromo-4-chloroanisole. We're going to start by drawing an anisole. So that's like a methoxybenzene. Put our methoxy. On carbons 2 and 6, we have bromine. So we have a bromine here, and we have a bromine here. And in the 4 position, we have a chlorine. The next one is metanitrophenol. We'll start by drawing a phenol. I always like to draw my group of my parent at the top like this. I don't know why. Anyhow, and then I always like to go clockwise. So 1, 2, 3, right? Meta is 1, 3 substitution. So there we go. Okay, I know I went over that pretty quick, but usually my students follow me by now. Let's switch gears and talk about the structure of benzene. And it says here that in 1866, Auguste Kekulé proposed the structure of benzene. That is a ring comprised of alternating double and single bonds. And I don't know if you've ever heard the story about the structure of benzene, but there's some interesting history to it because chemists knew the formula. They knew the C6H6 for quite a while, but they actually didn't have the structure. And there were other structures proposed. In fact, if you take a 6-membered ring, okay, like this, put 2 double bonds and then connect these 2 carbons like this. This is called benzene, and this is obviously not the structure of benzene, but it was one of those proposed structures. Another one, you're going to have to forgive me because I'm not a very good artist, but if you take, if you have like a triangle like this, and then you draw, right, if you have another triangle on top of it, does that work? You like this? This is called prismane, and that is also C6H6. That was also proposed. So it's not covered in our book, but just a little interesting history. And if you're like, well, why didn't they just run with those and say, that's the structure of benzene? Well, the reason why is because it didn't explain the reactivity or the lack of reactivity of benzene. And if you Google it, you'll find that there are other structures that I've forgotten. Anyhow, but Kekulé had this famous dream where he dreamt of a snake consuming itself by the tail, and he said, well, it must be a cyclic structure. I don't know how we got that to that quickly, but anyhow, he suggested that the exchange of double and single bonds was an equilibrium process. But we know that this is not, that it's not an equilibrium process, right? We know that this is not what's happening. We know that the benzene is actually in resonance, okay? And resonance is not an equilibrium process, okay? We now know that the 2 drawings are resonance contributors rather than in equilibrium. So in fact, we could even go back here, and why don't we just cross this out because they're not in equilibrium with each other. They are resonance structures. So what does that mean? That means that there are no double bonds and no single bonds in benzene. This is not a double bond. This is not a single bond. Like, what? Well, what is it? Well, if you look at the next structure, all of a sudden this is magically changed to a single, and this is magically changed to I was going to say a dingle. I mean a double. So anyhow, so what I'm getting at is that the bond order of all of the bonds, of all 6 of these carbon-carbon bonds, the bond order of each one of them, I'll put here BO, is equal to 1.5. They're all in between. They're a hybrid. They're somewhere between a double and a single bond. And that's why sometimes we like to draw a benzene ring with a circle in the middle like this to avoid drawing resonance structures. Now, there's an old joke, an old gag about somebody, putting this kind of structure up at a conference, and then somebody saying, why is there an oxygen inside of a cyclohexane? Anyhow, a little organic chemistry humor for you there. Okay, so that's what a resonance structure is. So remember, these 2 structures are not in equilibrium. There are no double bonds, and there are no single bonds in benzene. Okay, and we're going to talk about that a little bit more in a second. But before we do, it says here that aromatic rings, as I told you before, are remarkably stable. If you take an alkene, like cyclohexene that's shown here, and you treat it with bromine, well, first you form the bromonium ion, and then the other bromide comes in and attacks from the opposite face of the molecule, and you get an anti-addition. So you'd end up with this molecule here, plus you'd end up with the enantiomer as well. But it says here that if you do the same thing, or try the same thing, I should say, with an aromatic ring, you in fact get no reaction, no dice, nothing happens, okay? And the reason why is because of that inherent stability of benzene. Now, if we take a look at the heat of hydrogenation of 3 different compounds, so I want to draw your attention to these three compounds right here, right? It's kind of climbing up a stairway here of energy. If you take cyclohexene, so that's this molecule right here, and you hydrogenate it, well, you end up releasing 120 kilojoules per mole of energy. And the reason why is because a single bond is more stable than a double bond. And so you create cyclohexane, which is more stable. Okay, good enough. If you have this molecule here, which is 1,3-cyclohexadiene, so 1,3-cyclohexadiene, and you hydrogenate that, hey, what do you get? It's about double, right? About double the amount of energy is released because, hey, you're hydrogenating two double bonds. I'm thinking ahead here. Anyhow, you hydrogenate two double bonds. Now, this molecule here that's highlighted in red, that's not benzene. That's a hypothetical molecule. This is it's called cyclohexatriene. Okay, it doesn't exist, but you can imagine that if you were the person, going from 1 to 2 to 3 double bonds, right? You'd think, well, the heat of hydrogenation, I should release a lot more energy, right? There should be higher energy. Okay, but in fact, when you hydrogenate benzene, you find that there's a lot less heat energy released. In fact, even less than in the 1,3-cyclohexadiene. And if you're like, what are you getting at, Mr. Dion? The point of this slide is just to show you mathematically, or based on enthalpy, right, based on delta H, why, or that benzene is more stable than this hypothetical compound. So benzene has that inherent stability. Okay, now this is just looking at it in terms of delta H. We can examine it from another angle, and that is using MO theory. Now, oftentimes when I bring up MO theory, molecular orbital theory, students start rolling their eyes. And I'm not going to go into it in gory detail because MO theory can get quite complex. In fact, looking at how we get all the shapes of these different molecular orbitals involves complex mathematics. But the idea is this, okay, is that we can use a simplified version, or a simplified, how would I phrase it? Just examining it from a simplified viewpoint, we can explain how MO theory can help us rationalize aromatic stability. Okay, so we have 6 atomic p orbitals on the benzene molecule. And remember that when you have atomic orbitals, they will produce the same number of molecular orbitals. So we have the 6 p orbitals, right? Remember the shape of a p orbital? One of my students in 1401 said P for peanut. Okay, it looks like a peanut. Anyhow, so we have the 6 p orbitals, and they overlap, and they produce 6 different molecular orbitals. Okay, if we cut through the middle here, you can see that we have 3 bonding molecular orbitals that are lower in energy, and we have 3 anti-bonding molecular orbitals that are higher in energy. Now, using the Aufbau principle and Hund's rule, right, we start filling in the electrons, right, because each one of these p orbitals has 1 electron, right? 1, 2, 3, 4, 5, 6, right? We have those 6 electrons, okay, and we start pairing them up in these bonding molecular orbitals. And since all of the electrons are paired up in bonding molecular orbitals, we call that a closed shell configuration. Now let me move on. I'm probably getting ahead of myself here, but it just says here the locations of the nodes in the molecular orbitals and their shapes is based on high-level mathematics. We'll kind of skate over that. It says here that the delocalization of those 6 pi electrons, right? You have, right, think about it. You've got 3 double bonds, or at least that's what it looks like, right? So you've got a total of 1, 2, 3, 4, 5, 6 pi electrons, okay? I'm drawing them like this, 1, 2, 3, 4, 5, 6. You start pairing them up in the bonding molecular orbitals, 1, 2. So you'd start down here, right? 1, 2, 3, 4, 5, 6, okay? And again, they're all in bonding molecular orbitals, and that explains why benzene is so stable. And if you're like, well, would they ever be in non-bonding or anti-bonding molecular orbitals? Well, we'll look at that in a second. But the take-home message from here is just that those pi electrons are all in bonding molecular orbitals, and that is why benzene is, or is another explanation as to why benzene is so stable. Now, you might make a conclusion from that and say, okay, well, benzene has, 6 sides like this, and then it has alternating, double and single bonds, no matter how you draw the resonance structure. So maybe you'd think, okay, well, any ring that's got conjugation, and remember that conjugation is when you have double, single, double, single, double, single, so on and so forth. You might say, okay, well, anytime I've got conjugation in a ring, walla walla bing bang, there you go, that's aromatic, close the door, close the book, it's all done. figured it out. No, it's not true. In fact, if you look at these two molecules, cyclobutadiene and cyclooctatetraene, they're both fully conjugated, okay, but neither of them have aromatic stability. Neither of them have aromatic stability. Let me show you some examples, okay? It says here that some fully conjugated cyclic compounds react like normal alkenes. In fact, the example of that would be this molecule, cyclooctatetraene. If you take that guy and you treat it with bromine, it does an anti-addition to form this dibromo compound plus the enantiomer. And cyclobutadiene, it doesn't react in the exact same way that, it's reacting like an alkene. They're not showing an addition reaction, but they're showing what kind of reaction is this right here. This might be a little tricky for you to recognize, but this is actually a Diels-Alder reaction. So two molecules of cyclobutadiene will perform a Diels-Alder together. They form this three-membered ring, which is kind of wacky here, and then it rearranges to relieve that ring strain in the middle, and you end up with cyclooctatetraene. Okay, and if you're confused by like this and saying like, what's going on here? The point is that these two compounds are not aromatic, okay, and we're just showing a couple of reasons why, right? Because benzene doesn't react with itself, okay, doesn't do a Diels-Alder with itself. Benzene doesn't react with bromine. Okay, well, there's something wacky going on here. So first, let's examine the cyclobutadiene in greater detail. Now, it says here that in order for a compound to be aromatic, it has to meet two criteria. Okay, and if you're kind of in la-la land right now, I need you to wake up because this is very important, and oftentimes students might find this a little bit challenging. It says here, in order for a compound to be aromatic, it's got to have a fully conjugated ring with overlapping p orbitals. Well, this one has a fully conjugated ring. This one is fully conjugated with overlapping p orbitals. Well, what's the second rule then? The second rule is that it meets Huckel's rule. So Huckel's rule is that you have an odd number of electron pairs, okay, or 4n plus 2 total pi electrons, where n is an integer, and it can be 0, 1, 2, 3, 4, etc. Okay, so let's double check that benzene meets Huckel's rule. So first I'll draw the structure of benzene up here. Okay, so here's benzene. Okay, it's got 1, 2, 3 pi bonds. What does it say? An odd number of electron pairs. Here's a pair, here's a pair, here's a pair. That's 3 pairs. 3 is an odd number. What do you know? That meets Huckel's rule. Another way you could examine it is say, or 4n plus 2 total pi electrons. How many total pi electrons are there in benzene? There is a total of 6 pi electrons in benzene. Okay? Now, if I examine 4n plus 2, if n is equal to 0, 4 times 0 is 0, plus 2, we end up with 2 pi electrons. When n is equal to 1, I have 4 times 1, which is 4. 4 plus 2 is 6. That would be 6 pi electrons. Hey, what do you know? 6 pi electrons. That's a Huckel number. Okay, so either way that you examine it, it follows or it abides by Huckel's rule. Let's look at cyclobutadiene, and I'm sure you're way ahead of me, but you look at the number of electron pairs in cyclobutadiene. I have 1, 2. 2 is not an odd number. 2 is an even number. Also, how many total pi electrons are there in cyclobutadiene? There is a total of 4 pi electrons. Is that a Huckel number? Well, look, if we keep going, n is equal to 2. 2 times 4 is 8, plus 2 is 10 electrons. So we went over the number 4, okay? 4 wasn't even a consideration. So this is not an aromatic compound, so not aromatic, okay? And we're going to even more clearly define it in a few minutes. But for the same reason, cyclooctatetraene, which has 8 pi electrons, it's not a Huckel number of electrons. It's an even pair, an even number of pairs of electrons. So it's not aromatic either, okay? Give me a thumbs up if you follow me on Huckel's rule. Just Huckel's rule. I'm not asking for much more. Just, I kind of understand Huckel's rule. 4n plus 2. Yes, good. Every organic chemist has to know Huckel's rule. It's a classic. All right, well, here's what I was promising, is that we're going to examine these two compounds a little more closely. And we can use Huckel's rule using MO theory. If we look at the molecular orbitals for cyclobutadiene, okay, and here are the molecular orbitals drawn over here, it's got a total of 4 pi electrons. Now remember that electrons that are, or sorry, the molecular orbitals that are right in the middle, these are called non-bonding. Son of a gun. What did I do? Come on. There we go. So the molecular orbitals that are right in the middle, we call those non-bonding molecular orbitals. Anyhow, if we have a total of 4 pi electrons, right? We have 1, 2, and then using Hund's rule, right? Remember the bus rule? 1, 2. So that means you have 2 electrons that are unpaired in non-bonding orbitals. So that means that cyclobutadiene lacks a closed shell configuration. Remember, in order to have a closed shell configuration like benzene, you had all the pi electrons paired up in bonding molecular orbitals. And so this compound is actually anti-aromatic. Now let me say a little something about what anti-aromatic means. Anti-aromatic compounds are highly unstable. Okay, very, very unstable. And in fact, there aren't that many anti-aromatic compounds out there. If you Google it, trust me, you'll find some anti-aromatic compounds, but you'll find out like, hey, there's actually not that many. And let me explain to you very carefully why there aren't that many anti-aromatic compounds. Because what we're going to see as we move forward is that cyclooctatetraene, even though it doesn't obey the Huckel rule, it doesn't have a Huckel, it doesn't obey Huckel's rule, okay? Here's kind of Mr. Dion's summary of anti-aromatic versus non-aromatic. A molecule will do everything it can to avoid being anti-aromatic. Okay, it will do anything it can. Now the problem with cyclobutadiene is that it can't. Okay, it can't do it. It's got nothing. There's nothing it can do. Now, if you read the book, what it will tell you is that the cyclobutadiene will kind of adopt a rectangular shape like this. It'll kind of stretch like that, and that's to avoid the overlap of the p orbitals, but it's not enough. Okay, and so cyclobutadiene is an anti-aromatic compound. Now let's take a closer look at cyclooctatetraene, and this is a very specific example, and you will be asked to know this example. Okay, it says if you do the same kind of thing, the same molecular orbital analysis for cyclooctatetraene, it's got a total of 8 pi electrons. Here are the MOs. You get the bonding, the non-bonding, and the anti-bonding, and you can see that you have 2 unpaired electrons in non-bonding molecular orbitals. So it lacks that closed shell configuration. Okay, and you might think, okay, well, it's anti-aromatic, but in fact, it's not anti-aromatic. Okay, and you're like, well, why does it say anti-aromatic? Look, it says it suggests that it is also anti-aromatic. Now, before I, show you the answer, okay, which is on the next slide, remember, a molecule will do whatever it can to avoid being anti-aromatic because it's so high energy. And since cyclooctatetraene has kind of got that big 8-membered ring, what it can do is what's shown right here. Okay, it kind of bends. Okay, so it kind of bends like this, kind of bends up like this and up like that, and we call that a tub shape. Okay, you can imagine yourself like just relaxing in the tub here. Anyhow, you're like taking a bath. Okay, so it's got a tub shape to it, and what that tub shape does is it prevents the conjugation from occurring. And if you're like, what's conjugation? Well, I've gone over that, but it prevents the efficient overlap of the p orbitals. So what that means is that you might have overlap here and you might have overlap here, but because of this funky angle here, it won't be able to overlap, properly. And so this is a specific example that you need to know. So you need to know this example, the cyclooctatetraene. The conjugation does not extend around the entire ring, so the system is neither aromatic or anti-aromatic. It is non-aromatic. And so moving forward, we're going to see 3 types of aromaticity. We're going to see aromatic, okay, anti-aromatic, which again, there are very few anti-aromatic compounds, and we're going to see non-aromatic. Okay, so most of the time, we're going to look at aromatics and non-aromatics, but we will see anti-aromatics as well. All right. The stability of benzene. If you want to be able to predict the stability of benzene using molecular orbital theory, you don't have to get involved in any kind of complex mathematics. You can use what's called a Frost circle, which was developed by Arthur Frost. I'm never going to ask you to draw a Frost circle. In fact, our next quiz will be multiple choice, but what you do is you start by drawing a circle. Okay, so you draw a circle. Everybody can draw a circle, right? Then what you do is you put the polygon that is the shape of the ring you want to consider inside the polygon, and you make sure that one of the points connects the very bottom of the circle. Now, everywhere that there's a point intersecting that circle, you draw a horizontal line, and that represents all of the molecular orbitals. You draw a line through the center of the circle, okay, like this. Everything that's above the line is a non-bonding molecular, an anti-bonding molecular orbital. Everything that's below it is a bonding, not in this particular example, but if you did end up with some that were right on the line, of course, those would be non-bonding molecular orbitals. So this is a pretty brilliant, discovery, or a way to propose, to help explain MO theory. And in fact, Frost circles help us understand the n+2 rule, because if you look at going from a 4-membered ring, so this is a 4-membered ring, all the way up to a 10-membered ring, if you look at the number of bonding molecular orbitals for all of these rings, 4, 5, 6, 7, 8, 9, 10 membered rings, you can see that here we have one bonding molecular orbital, right? That can hold a maximum of 2 pi electrons. Well, 4n plus 2, when n is equal to 0, right, we end up with 2 pi electrons. Hey, what do you know? 2 pi electrons. When n is equal to 1, right, 4 times 1 is 4, plus 2 is 6. 6 pi electrons. Hey, look, here we'd have 6 pi electrons. Here we'd have 6. Here we'd have 6. Here we'd have 6. Okay? And when n is equal to 2, right, 2 times 4 is 8, plus 2 is 10. 10 pi electrons. Well, look at the last two. You'd have a total of 10 pi electrons and 10 pi electrons, like that. Pretty cool, huh? Note that the number of bonding orbitals is always an odd number. Aromatic compounds will always have an odd number of electron pairs. All right, so Frost circle is kind of cool, huh? All right, so it says here a little bit more of a summary about anti-aromatic compounds and aromatic compounds. Let's go through it before we start identifying some more aromatic compounds. It says here that aromatic compounds fulfill 2 criteria. And we've already gone over this, but let's go over it again. They have to have a fully conjugated ring of overlapping p orbitals, and it has to meet Huckel's rule, has an odd number of electron pairs, or 4n plus 2 total pi electrons, where n is 1, 0, 1, 2, 3, 4, 5, whatever. Anti-aromatic compounds fulfill 2 criteria. A fully conjugated ring, overlapping p orbitals. You're like, that's the same rule as the first one, yeah? Anyhow, but they have an even number of electron pairs. So instead of 4n plus 2, you have 4n, okay? So if you have 4n where n is equal to 0, you'd have 0. So that doesn't work, so we'll just delete that. If you have 4n where n is equal to 1, you'd have 4 pi electrons. If you have n is equal to 2, you'd have 8 pi electrons. If you have n is equal to 3, you'd have 12 pi electrons, so on and so forth. Now, it says here that when a compound fails criteria number 1, it's non-aromatic. And I'll be honest with you, I've taught this class long enough to know that I shouldn't say that. Oftentimes, students will not get this on the first try. They'll get kind of muddled and kind of muddied up here. But you'll find that if you practice and take a look at all the examples that are in the textbook, it will become clear to you, okay? It gets really clear to students after they take a good hard look at it. Here are some other molecules. Now, 6-annuline is simply benzene, so that's an aromatic compound. But if you have another conjugated ring here, like this molecule 10-annuline in the middle, it says here that these compounds can be aromatic, anti-aromatic, or non-aromatic. And you might think, okay, well, benzene is aromatic. We already know that. We've discussed that in gross and dirty detail, so aromatic, okay? But 10-annuline, okay, if you think about 10-annuline, you look at the number of pairs, okay, so we have 1, 2, 3, 4, 5. Hey, that's an odd number of electron pairs. It's got 10 pi electrons. Is that a Huckel number? Well, yeah. If we have 4n plus 2 and n is equal to 2, then we have 2 times 4, which is 8 plus 2. So we'd have 10 pi electrons. So you might think, hey, man, aromatic, baby. Aromatic. Let's move on with life. In fact, it's not. So I'm going to erase that. It's not aromatic. Okay. It's not anti-aromatic because it doesn't have a 4n number of pi electrons. And you're like, well, why is it non-aromatic? It's because of the hydrogens here and here. You see how I can't even draw them without overlapping them? Okay, let me try to do it a little prettier. Okay, so you see that you have a hydrogen coming down here and you have another hydrogen coming like that. And so what they do is they create a steric hindrance here, which pushes the molecule out of planarity. So it's not totally flat. And if it's not totally flat, that means that all of those p orbitals cannot overlap efficiently. And so this molecule is non-aromatic. Okay, non-aromatic. Now you might think with 14 annuline, you might think, well, shouldn't you have the same problem because you got a hydrogen here, you get another one coming in here, you get another one here, and you get another one here. But the answer is that this is aromatic. I know it's going to annoy you, but this is aromatic. You're like, well, why is that one aromatic? And the reason is probably exactly what you're thinking, is that the molecule is so big that there is a lot less steric hindrance. It pushes the molecule slightly out of plane, but it's still planar enough that this remains an aromatic compound. And so I'd say the take-home message, if I really only had 30 seconds to explain this slide to you, I'd say you should know this exception right here, is that 10 annuline, based on those 2 hydrogens in the middle and their steric repulsion, there we go. All right, so doesn't 10 annuline have 5 pairs of electrons? Yes, it does, okay, which is an odd number of electron pairs. Okay, so we have to have an odd number of electron pairs, just like benzene, which has 3. Right here you have 1, 2, 3, 4, 5, 6, 7, an odd number of electron pairs. All right, there we go. So all of these molecules satisfy the Huckel number of electrons, right? But for a different reason, which is the steric hindrance, 10 annuline is a non-aromatic compound. All right, well, let's move on from there and talk about other aromatic compounds. It says here that aromatic rings can contain carbanions and carbocations. So we're going to look at 2 specific examples, one where we have a carbanion and one where we have a carbocation. So if you have a 5-membered ring, okay, a 5-membered ring, here's a beautiful frost circle. We've got 3 bonding molecular orbitals, and what can it take on? It can take on a total of 1, 2, 3, 4, 5, 6 pi electrons. Okay, so you've got to have 6 pi electrons in there in order for it to be aromatic. Now you might be thinking, well, how the heck? I can't do this. I can't put 2 pi bonds adjacent like that. That's insane in a ring. So there's got to be another answer. Well, we're going to see what that answer is right now. Okay, so if we had a cyclopentadienyl anion, and so if we ripped off a proton, or if that molecule, cyclopentadiene, that's this guy here. Okay, so this is cyclopentadiene. Okay, if you remove one of these 2 protons, okay, you end up with the cyclopentadienyl anion, the conjugate base. Okay, nothing more than that. If you look at it, it's got 5 resonance structures. So the cyclopentadienyl anion has a lone pair delocalized over each of the 5 carbon atoms and is an aromatic anion. Now you might be wondering, why the heck is this aromatic? And we're going to explain this in a second. But I want to also talk about the pKa of this molecule. You think about hydrocarbons, right? The hydrocarbons usually have really high pKa's, up in the range of 40s and 50s, or high 40s and 50s, okay? So really high pKa's. You look at this, it's got the same pKa as water, for Pete's sake. And you're like, well, why would that, be so acidic? Because it wants to lose that proton badly, because you go from a compound that is not aromatic. So this is not, it's just not even an aromatic compound. So not aromatic in any way, okay? To something that's aromatic, right? And we said that aromatic compounds are stable. Okay, so that anion itself is aromatic. And if you're wondering, well, why would that be? I got this guy here, right? This carbon. If I think about this carbon that I have highlighted in yellow, it's got 3 sigma bonds and a low pair. Isn't it sp3 hybridized? How would I have a continuously overlapping system of p orbitals? Well, the answer to that is a pair of electrons, or sorry, the molecule will adopt the hybridization, the atom will adopt the hybridization that it has to in order to achieve aromaticity. And so this lone pair that's shown right here, this lone pair is actually in a p orbital, okay? And if it's in a p orbital, that renders this carbon sp2 hybridized, not hydridized. I got hydroniums on the brain from talking about too much Gen Chem. So hybridized, okay? And I'm going to come back to this in a second, okay? But before we do that, let's look at another example, okay? You know what? Before I get onto that, let me talk about this a little bit more, okay? So if those two electrons, if that lone pair, that negative charge, if that was in a p orbital, right, then I would have a continuously overlapping system of p orbitals. Look, if you think of your pi bonds, okay, you have a p orbital here, another one here, another one here, another one here, another one here. And then if that carbon is sp2 hybridized with the lone pair, you have 1, 2, 3, 4, 5, 6 electrons in there. Anyhow, let me keep moving and talk about the tropylium ion. So if you have a 7-membered ring, the 7-membered ring has 3 bonding molecular orbitals. So if it has 6 pi electrons and one of the carbons has an empty p orbital, then the compound is going to be cationic, but it's also going to be aromatic, okay? And let's see why that is. So if you look at this molecule, so the tropylium cation, you have to know the tropylium cation, and you should know that it is aromatic, okay? And the reason why is because if you think about this molecule, and I'll draw it down here, okay, this cation, okay, here's my 7-membered ring, okay? I'm going to draw it just like it's drawn here. So this carbon is easy to see is sp2 hybridized, right? It's a carbocation. So that means it's got an unhybridized p orbital, right? And every single one of the other 6 carbons in the molecule, those also have p orbitals in them, right? 1, 2, 3, 4, 5, 6. So does it meet the criteria? It's got a continuously overlapping system of p orbitals, right? Perfectly overlapping system of p orbitals, and it has a Huckel number of electrons, 4n plus 2, when n is equal to 1. That's one way you can think of it. Or it's got an odd number of electron pairs, right? So that renders this an aromatic cation. All right. Now, what about aromatic heterocycles? So we're getting into even heavier molecules or more interesting molecules that have are aromatic. If you look at these two molecules, pyridine and pyrrole, they're both aromatic, but for very different reasons, okay? And both of these nitrogens have a lone pair, right? This nitrogen has a lone pair, and this nitrogen in pyrrole also has a lone pair, okay? But the difference is this. The lone pair on the nitrogen in pyridine is in an sp2 hybridized orbital, right? Because there already is a pi bond on that nitrogen, so it already has a p orbital. Whereas the lone pair on pyrrole is in a p orbital. Now, why would it be, if you're like, well, I'm struggling here, why would it be different? Because a molecule will do what it's got to do to become aromatic. Pyridine is already an aromatic compound, right? You can see it's got the 3 double bonds, just like benzene. They alternate, so you have a continuously overlapping system of p orbitals. You have a Huckel number of pi electrons. Great. But if you look at pyrrole, you might think, well, here's pi electrons and here pi electrons. That doesn't obey Huckel's rule. It's only 4, right? That would be anti-aromatic. No, because this lone pair that I have highlighted in yellow, the red pair, okay, if those go into a p orbital, then what do I have? I have a continuously overlapping system of p orbitals. And if those are in p orbitals, those are considered like pi electrons, right? So now I have 1, 2, 3, 4, and 5, 6, which is a Huckel number of pi electrons. And so that renders pyrrole aromatic, okay? Give me a thumbs up if you're even 60% of the way with me on that. As I admit, it's not a simple concept. 50% of the way? All right, even half of the way. Look, if you're the kind of person who, absorbs a lot of information in class, I think that's great. But I'll just give you a heads up on this. Usually students will have to backtrack, go back to the book, look over it a couple of times before they understand why both of these compounds are aromatic, but for different reasons. Now, continuing on in that same vein, it says here, if the heteroatom's lone pair is necessary for aromaticity, it will be included in the Huckel number of pi electrons. So that's basically what I was just telling you. This is Dr. Klein's summary of Mr. Dion saying a molecule will do, or lone pair will do what it's got to do to make a molecule aromatic. Okay, let's move on from there and talk about the basicity of these two compounds. Now, pyridine is a base. Okay, pyridine is a base. I just want to make sure you know which one is pyridine. So here's pyridine. Okay, and why is pyridine a base? Because the lone pair is available, right? If the lone pair accepts a proton, which is the Bronsted definition of a base, you still have an aromatic compound, right? Beautifully aromatic. But the thing is, the reason why pyrrole is not an aromatic compound is because when the lone pair here, which is required, I'll put it here, required for aromaticity, when that takes on a proton, you make something that's non-aromatic, so it's not going to want to do that, right? And that's going to drop the pKa dramatically. It's like, get me rid of that proton. I don't want that proton. I want to be aromatic, man. All right? Okay. Well, here's just an electrostatic potential map of pyrrole and pyridine. And you can see that in pyridine, that lone pair, this lone pair here is localized, right? And it even says it right here. Why am I pointing it out a second time? Anyhow, that lone pair is localized. So you have all that partial negative charge there, whereas this lone pair is involved in or is part of the continuously overlapping system of p orbitals. And so it is completely delocalized, right? It's delocalized between all of those p orbitals. And that's why we see, that partial negative charge all over the ring. Okay, like that. Okay. Well, with that in mind, let's give this one the old college try. It's 8:59. We've got 3 hours left. Let's go for it. Decide whether each of the following is aromatic, non-aromatic, or anti-aromatic. Let's do the first one. Okay. You can see that we have 2 pi electrons here, and then we have 2 electrons here. Okay. That can be in a p orbital. So if this carbon is sp2 hybridized, right? If that carbon is sp2 hybridized, then this lone pair would be in a p orbital. We'd have a continuously overlapping system of p orbitals, but we'd have a total of 4 pi electrons. And 4 pi electrons, when 4n, and when n is equal to 1, we get 4 pi electrons. And you remember that 4n, when the 4n rule is obeyed, this compound is anti-aromatic. Okay, so this is an anti-aromatic compound. If we take a look at the next one, and I'm going to draw it a little bit bigger here, just to help understand what the heck is going on. Okay, we have a carbocation here. Okay, well, let's think about the hybridization of each one of those carbons. The carbocation is sp2 hybridized. That means it's got a p orbital. Right, these 2 carbons are both involved in a pi bond, right? So these are both sp2 hybridized, right? These are both sp2, so means they both have a p orbital. How many pi electrons do we have? We have the 2 in the double bond. That's it. Okay. Well, does that follow Huckel's rule? When 4n plus 2, when n is equal to 0, we have a total of 2 pi electrons. So does this abide by Huckel's rule? The answer is yes. We have a continuously overlapping system of p orbitals, and we have a Huckel number of pi electrons. And so this compound is, in fact, aromatic, like that. Okay, let me move that guy out of the way a little bit. It didn't help, did it? All right, while I'm working here, you guys can take a look at the next one. I'm working my iPad magic. What about the next one? Would this one be, does anybody have a guess? Or I shouldn't say guess. Does anybody have an educated guess, a hypothesis that they would put forth about the next one? Yeah, somebody says anti-aromatic. Okay, well, let's take a look at it. If you think about it, this molecule, and I will redraw it down here, okay, just so I can scribble all over it. Okay, if this is a carbocation, every carbon in here is sp2 hybridized. So all carbons are sp2. And what does that mean? That means that every stinking one of them has an unhybridized p orbital. 1, 2, 3, 4, 5. So do I have a continuously overlapping system of p orbitals? You bet your bobby socks I do. Do I have a Huckel number of pi electrons? Well, I've got a total of 4 pi electrons. Okay, I've got a total, right? I've got 1, 2, 3, 4. That's a total of 4 pi electrons. So 4 pi electrons. 4 pi is not a Huckel number. Remember, Huckel numbers were 2, 6, 10, so on and so forth. This is actually a 4n when n is equal to 1. And so this molecule is anti-aromatic. Anti-aromatic. All right, let's try the last one. Does anybody want to wager anything for the last one? It's anti-aromatic, aromatic, or non-aromatic? Or do you want me to just walk you through it? Okay, let's take a look at it. Let's take a look at this one here, okay? So David says, what would it be if you had a methylene group? So if you have this compound here, this is just cyclopentadiene, that's non-aromatic, or it's not aromatic at all, okay? You don't even have to consider that because this is sp3 hybridized, okay? Doesn't have a continuously overlapping system of p orbitals. All right, so somebody says that this next one or this last one is aromatic. Let's take a look at it. If this carbon was sp2 hybridized and that lone pair was in a p orbital, then we'd have a continuously overlapping system of p orbitals. Forgive my artistry here, okay? Then you'd have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pi electrons, okay? Now remember, if a lone pair, this lone pair, if it goes into that p orbital, then you've got a Huckel number of electrons, right? You've got 4n plus 2, where n is equal to 2. Then you have 10 pi electrons, and that would render this molecule aromatic, okay? A molecule will become aromatic if it can. And if you're like, well, why do you know that, Mr. Dion? Well, look, let's go back here. Okay, and that's this point right here. And after years of teaching this class, I think this is probably the most challenging rule, okay, in this whole chapter is this one right here. If the heteroatom's lone pair is necessary for aromaticity, it's going to be included in the Huckel number of pi electrons, okay? It will do it if it needs it. All right, let's take a look at some more examples in 17.5. Okay, this is one of those days when you got to read the chapter before coming to class, right? Which I know you always do. You're sitting at home, reading the book with bated breath, hanging on every word that Dr. Klein has to, say. 17.13, for each of the following compounds, determine which, if any, of the lone pairs is participating in aromaticity. So now we're going to get some practice on that rule that I just told you was, one of the more difficult rules in this chapter. Okay, so let's look at this first molecule. And if you're like, what's going on? Okay, let me draw the molecule. Okay, if I drew a water molecule for you, right, like this, okay, what's the hybridization of the oxygen and water? It's sp3, right? That's old chemistry. That's the first chapter of Organic Chemistry 1. That's general chemistry. That's general chemistry 1, hybridization. Okay, and so you might just look at this oxygen and say, hey, Gen Chem baby, Chem 1, that's sp3. What I'm saying is that if the two lone pairs, if those both stay in sp3 orbitals, okay, that's fine. But if that oxygen is sp2 hybridized, that would mean that one of these lone pairs goes into an unhybridized p orbital. Will it do it? Nah. I put the or here, right? Because of this rule. If the heteroatoms lone pair is necessary for aromaticity, it's going to be included in the Huckel number. Okay, and it will actually change the hybridization of that atom to something different than you might think it would be. And so my question to you is this compound, or I guess the question is that question that's asked, is that lone pair, is one of those lone pairs participating in aromaticity, yes or no? Is this a yay or a nay? Yes, it is, right? Because if those two electrons go into a p orbital, then I've got a p orbital here, I've got one here, I've got one here, I've got one here, I've got one here. How many total pi electrons would I have? 1, 2, 3, 4, 5, 6. 6 is a Huckel number, right? 6, if I have 4n plus 2, when n is equal to 1, I have 6 pi electrons, okay, and that's a Huckel number, and therefore this lone pair is participating, and you could circle either one, doesn't matter, but the answer here would be yes, okay? Yes, a lone pair is participating in aromaticity. Let's skip B and we'll move right to C. Okay, let's move right to C, and I'll redraw the molecule the best I can. Does anybody else find it challenging to draw 7-membered rings? Probably just me. Anyhow, there's a good halfway decent 7-membered ring. Okay, so what the question is asking is this lone pair that I'm highlighting in red, is this participating in aromaticity, yes or no? Do you think this lone pair is participating in aromaticity, yes or no? Okay, I get some people saying no, and I think that those people are on the right track, because hypothetically, if it was, you'd have p orbital, p orbital, p orbital, p orbital, p orbital, p orbital, right? There. And if it was, okay, and it's not, but if it was, okay, so don't draw what I'm drawing here, you'd have a total of what? 1, 2, 3, 4, 5, 6, 7, 8 pi electrons. That's not a Huckel number. That's 4n when n is equal to 2, right? Then you'd have 8 pi electrons. That would make it anti-aromatic, okay? Remember, a molecule will do whatever the hell, pardon my language, whatever it can to avoid being anti-aromatic. And so that pair of electrons, okay, is not going to be in a p orbital. In fact, they are going to be sp3 hybridized. So we'll put here sp3, so that it's not anti-aromatic, it is non-aromatic. All right. Hopefully that clears it up a little bit. Seemed like I got some pretty quick answers on that one. Well, I'll just ask you E quickly, without even me redrawing E. What do you think? The lone pair in E, if I highlight it in yellow, are those participating in aromaticity, yes or no? Based on your, go with your gut feeling. Not all the time, but some of the time it's safe to do that. What do you think? The lone pair on the oxygen? Yeah, I see somebody says no. Anybody else have any thoughts? Yeah, the answer is no, right? Because there's already a pi bond right here between this carbon and the oxygen. So there's already a p orbital here involved in this pi bond. So you've got a continuously overlapping system of p orbitals like that, and you have what? You've got 1, 2, 3, 4, 5, 6 pi electrons. That's a Huckel number. Okay, so that lone pair here, that has got nothing to do with aromaticity, just like the example with pyridine. Okay, and so this molecule is aromatic. Okay, and the answer is no. These are not participating in aromaticity. So the answer was yes for the first one, no for this one. Okay. All right. This molecule here is called thiazole. Thiazole. Why don't we do that next class? And we'll do the other one next class. I just want to talk about polycyclic aromatic compounds. No, let's go back to this. Let's go back to this. I'm gonna have to erase some of this stuff. Let's try B. Okay, let's stick on the same thing. Okay, instead of jumping to something new at the end of a lecture. Let me just delete this. Delete. So what about B? If I draw structure of this molecule here, thiophene, it's got 2 lone pairs. Are either of those lone pairs participating in aromaticity? Not a trick question. Yeah, the answer is yes. Absolutely right, because if one of them goes into a p orbital, then I have a continuously overlapping system of p orbitals like that, and then I have a total of 1, 2, 3, 4, 5, 6 pi electrons, which is a Huckel number. And so the answer to this one is yes. All right, and let's try the last one, the thiazole, and then I think we'll wrap it up for the day. Just delete this guy for now. What am I talking about? Permanently. There we go. So let me redraw this molecule like that. Oh, we've got a bunch of lone pairs here. Maybe I'll highlight them in different colors. So if I have yellow, these ones, and then if I highlight the lone pair on the nitrogen, are any of these participating in aromaticity? Somebody says sulfurs. Yeah, Andrew, thank you. Yeah, Andrew says sulfur's lone pair, one of the lone pairs is participating in aromaticity, right? This lone pair not participating. So not participating. Why? Because there's already a pi bond right here. There's already 2 p orbitals, right? There's one here and there's one here, okay? If one of those lone pairs is in a p orbital, I have pi bond here, so p orbital there. Then I have a continuously overlapping system of p orbitals, and I have a total of what? 1, 2, 3, 4, 5, 6 pi electrons, which is a Huckel number. And so the answer is one of these, yes, and this one, no, like that. Okay, there we go. Now, if you find this tricky, what I would recommend is reading the book before coming to class on Friday so that you can cement, or more your knowledge of aromaticity. So next class, we are going to finish up the chapter. And if you're the kind of person who's like, give me back to reactions. I like just learning new reactions. Well, the good news is next class, we're going to look at a bunch of new reactions and some you've seen before that we'll look at in even more detail. So 17.6 and 17.7 deal with reactions. And at the end, if there's time, we might talk about the spectroscopy of aromatic compounds just as a refresher. And whatever time we have left over, we'll take a look at some practice problems as a group.